I welcome you all in this course Introduction to Sequence Stratigraphy, and in continuation to our discussions on phasis analysis and its application in interpretation of depositional environment, we introduced a term called phasis models. So, in this class we are going to discuss about phasis model. However, phasis model is a very vast subject area, because for each and every depositional environment we can have separate phasis models, and which also can vary from environment to environment depending on the control factors. However, in this particular class I will try to give you a brief idea about what is actually meant by phasis models and how we can understand different environmental processes, or how we can represent a depositional environment through phasis models. So, phasis models, these are presented in ideal stratigraphic columns. So, it may be a clubbing of several columns from one depositional environment, and in that column we try to represent the occurrence of all the phasis types which are available, which are present in that particular sedimentary environment. So, a phasis model commonly express general statements about a depositional setting. For example, if it is a fluvial environment, what are the conditions prevailing over there, what are the nature of sedimentation, and what are the final products. Through phasis model, we can filter the local sedimentary and stratigraphic variations which are encountered from one set of exposures to the next one. Similarly, we can also get idea about the phasis and phasis associations which are altogether present in that particular depositional environment. So, we can predict about what will be the possible phasis, what will be the possible phasis associations, and such prediction in turn help us to interpret about the similar kind of conditions available in other successions. Basically, a phasis model act as a norm for all such deposits. So, when I am talking about a fluvial phasis model, it will be kind of an ideal model which should be for an fluvial depositional environment, and based on that particular model I can compare it with any predicted fluvial depositional model. Say from one area we are expecting that possibly this is a fluvial depositional model. So, we can straightway refer to the fluvial phasis model, which is an ideal one, a normative one, and we can compare it, and from there we can come to a conclusion that yes, this particular depositional environment which we are interpreting is a fluvial environment. So, in this class I will try to give you a brief overview of some of the depositional environments in terms of their phasis models. So, definitely it is not possible to go into the detail of each and every environment, because each and every environment is distinct in terms of the processes and the responses. So, I will just pick up some of the environments, and from there I will try to give you what are the ideal phasis model for that particular environment and how they form, or in terms of the processes how we can interpret them. So, the first example that I am taking over here is a fluvial environment. So, this is the phasis model for a fluvial environment, and as we all know that fluvial systems, fluvial depositional environment can broadly be divided into several types of river systems. The most common one is a braided river and a meandering river. So, here in this particular example I am trying to show you what are the phasis models for a classic braided channel deposit and a classic meandered channel deposit, and what are the differences between them. To understand this phasis model, we have to first understand that what are the processes that goes on within a braided channel system and a meandering channel system. As we all know that if we draw a braided channel system, it is not meandering in nature, so it is not sinuous in nature, but within the channel system we get several braid bars which form over here, and through them the channel flows like this. So, it looks like this. So, in this kind of condition, when a channel is flowing through this and some bars are forming in between, which are large bars, commonly they form in the upper reach of the river, upstream part of the river, where the energy condition of the river is relatively high and it is carrying coarser sediments dominantly, particularly in the bed load, However, finer sediments are also available, but they are mostly transported in the suspension load. So, in such kind of condition, when we have very coarse grained sediments, clastics present in the bed load of the river, so we expect their deposition within these bar systems. So, what can be the possible facies types that we can expect? Definitely we can expect some conglomerates, very thick pebble or even larger grain bearing conglomerate beds formed at the base of this kind of braid bar. So, if I just want to understand what will be the nature of facies types within one such braid bar, definitely it will be repetitive in all of these braid bars. So, if we try to understand how it forms, so basically that will give us the model for a braided river system. So, in case of one braid bar, what we can expect? Initially, it will start with some very coarse grained sediments which will be deposited at the basal part of the braid bars, and then it is going through or it is forming through some high energy current system which is carrying sand after this first load deposition. So, definitely those sands will be deposited forming large bed forms. So, maybe dune scale bed forms or large 3D ripples which commonly form in high energy condition. So, when such larger bed forms will migrate, the kind of crossbed we expect is trough crossbedding, and that is also in very large scale. So, in terms of meters to several tens of meters in that scale, we expect formation of trough cross stratification. So, we get trough cross stratification of different types and they starts amalgamating one after another. So, in that way we get one phase of deposition of braid bar along with the river flow. Since it is a very dynamic system and water is flowing, so it will always try to erode or deposit materials. So, when a flow is getting diverted or distributed like this, so in one part we can get a major flow going, another part maybe a little amount of flow is going on. So, definitely from this part where the main flow is going on, there we have the major sediment load. So, we can expect more deposition over here depending on how this braid bar is getting affected by the flow. So, maybe in the initial part over here in this part, maybe in this case we can get initially erosions which can be expected through formation of this kind of erosional surfaces within the braid bars, maybe eroding some of the deposits which are already formed, and then we get further deposition in the form of another conglomerate bed. So, in that way the braid bar gradually grows up as well as it moves forward, it progrades, and that progression can be laterally as well as along the channel. So, a braid bar formed like this, it can migrate in this direction as well as it can migrate in this direction depending on how the deposition is going on, in which direction the flow is depositing the sediments. So, what we expect? Repetition of this kind of unit one after another forming the braid bar, and same kind of condition we can expect in all these braid bars. So, basically one such unit will represent a braid bar system within a braided channel deposit. Definitely it will associated with or it will alternate with the overbank portions, where during occasional floods we can get some stagnant water body developed over there and we can get some floodplain deposits. A completely different scenario we can expect in case of a meandered channel deposit. Normally meandered channel deposit forms when the river strength, flow strength is reduced. So, normally it is much distant from the source area, and there it is mostly in the planar part where the sediment load is dominantly sand or mud. So, availability of finer grain sediments actually makes its banks more stable, and that is why the river starts meandering. Instead of making these bars in between the channels, it starts meandering like this. This kind of meander channel forms, and within this kind of meander channels the flow it moves like this, and as a result of that we get more erosions along this bank and deposition along this bank. So, what we get over here is a point bar which forms along one bank of the channel, which again alternates. Along this bank we get mostly erosions, and here along this bank we get deposition. So, with time if I try to draw a section of the channel, it looks like this. This is asymmetrical channel, because in this part we are getting deposition of point bar, whereas in this part we are getting erosion, and so the river channel is gradually moving back like this. So, at any given time we can get some deposition occurring over here within the point bar, which is represented in this part, and very occasionally we get flooding events, and that flooding will cover up the associated floodplain areas, which we call as the overbank areas, and in that overbank area we get dominantly mud depositing condition. Similar kind of condition can occur when due to excessive erosion we get a channel abandonment. Say for example, if the channel is like this, meander channel is like this, then we can get excessive erosion over here, and after some time we can get a channel is changed like this. So, the river will now flow along this direction. So, this part of the channel is abandoned now. So, initially in that abandoned channel sand was deposited, but as the flow is stopped, so now it is a stagnant water body, and in that stagnant water body we get deposition of this kind of sand mud alternation initially, followed by mud deposition, which will be also in case of when there is a flooding. So, each and every point bar is covered up by this kind of overbank deposits, which is dominantly mud depositing condition, whereas the point bar itself forming within the channel starts with some coarse grain material at the base, maybe some channel lag deposit which forms at the base of the channel along this part, and on that gradually we get lateral accretion of cross bedded units. We call them as lateral accretion surface or lateral accretion elements. So, along those surfaces continuously the accretion of point bar system develops. So, as a result of that, what we get is a continuous sand deposition for each and every unit, but the nature of facies types within that sand unit that varies from base to top, as the energy condition is varying from base to top. So, within one point bar deposit we can expect a deposition of sediments like this, assemblage of facies types like this, and we can expect all such point bars. So, another point bar forming over here in this part, another point bar forming somewhere here maybe in this part, everywhere we can expect same kind of facies model to develop. So, one meander channel deposit can be represented by stacking of similar kind of point bar deposits and associated overbank or the abundant channel deposits. In the exposures, what we will get? So, there will be not laterally continuous units, but there will be isolated stacked units one after another, which will indicate this kind of shifting of the channel due to point bar migrations, due to the meander channel migration, and point bars will be overlain by this kind of overbank deposits. If we look into another sedimentary environment, say for example a shore environment, or more commonly we call it as the beach environment. So, within shore environment, if I draw a shore environment, it looks like this, where we can get these waves are coming in. So, within this part we divide this entire shore environment into several sub zones or sub environments like back shore environment, then foreshore, shore face, offshore transition, and finally offshore, which is mostly done by 4 parameters: average high water level, average low water level, then the average fair weather wave base, and the average storm weather wave base. So, based on these, say if this is the mean high water level and this is the mean low water level, so this portion is called as the foreshore area. Then the area from mean low water level to the fair weather wave base, that portion is called as the shore face area. Then comes the offshore transition, which extends up to storm weather wave base, and beyond storm weather wave base we get the offshore area. Beyond the foreshore area we get backshore. So, basically this foreshore area, it is between the fluctuation of water levels between high water level and low water level over a significant amount of time interval. So, we take the mean high water level and mean low water level. Similarly, shore face area, it is above the wave base, so always it is under wave action. And then comes the offshore transition, where we get not normally the fair weather condition, but it can be under wave action when there is a storm. And then comes the offshore area, which is beyond the storm wave base. Even during the storm, it is not affected by waves. So, what are the processes going on over here in terms of the agents? So, definitely the main agent is wave. So, waves are coming in towards the land, and as that wave is reaching towards the shoreline. From there we get two different currents are forming. If this is the shoreline, then as the waves are coming in like this, then based on this wave propagation direction and also on the orientation of the shoreline, we can get two different currents forming. One near parallel to the shore, which we call as the longshore current, another one near perpendicular to the shore, which we call as rip current. So these two currents are solely responsible for the reworking and distribution of sediments from shoreline to the offshore direction. So the transportation of sedimentation, collecting the sediments starts from here, and basically the sediments are actually transported or supplied by the river systems, which get distributed by these waves and longshore currents along the coastline, and from there rip currents, they brings the sediments towards the deeper part. So definitely the energy condition is much higher over here, and as the flow rip current will come down the slope, gradually it will drop its sediments and it will also lose its energy. So we can expect more finer grain sediments as we go away from the shoreline. So in the offshore part, we expect dominantly mud depositing condition, whereas in the shore face or foreshore, it is dominantly sand, and also the type of sand, nature of sand deposits, the facies types will vary. So at any point of time, we expect that this entire system should move in this direction, so that we can get gradually one unit coming over the another one following Walther's law. So if we try to understand what are the different facies types in individual sub environment, in the offshore area, as I told you, this is a very low energy condition. So we commonly get mudstone, which is highly burrowed, and sometimes during some storms, high energy storms, we can get little bit of supply of sand in between the dominant mud. So this area is dominantly mud depositing condition. On the offshore area, we get a shore face area, and in this shore face area, particularly when we talk about the lower part of the shore face, that means near to the offshore. So in that part, dominantly we get proximal storm beds, which is carrying lot of sand into the system. So we get dominantly sand deposits, and since these are associated with storm or led by storm, so we get hummocky, swelly, cross stratified units as well as wave ripples, sometimes maybe combined flow ripples, and then they are associated with mudstone interbeds, particularly when it is not affected by storms. So when it is not affected by storm, basically it is a very low energy condition. So during those times, dominantly mud is getting deposited, because rip current is not supplying sand up to this distance. In contrary to that, if we look into the upper shore face, which is much closer to the shoreline, so there we are getting more frequent supply of sand by the rip current itself. It is above the fair weather wave base, so it can get affected by the storm events, storm surges, as well as it is regularly affected by fair weather waves, and the sediments are supplied by the rip currents. So very regularly sediments are coming in and getting deposited over here through channel systems. So what we expect, thick sand beds with this kind of trough cross stratified sandstones. And then we get the foreshore area, where again we are getting sand beds, but here the dynamics is completely different, where every now and then waves are coming in and then they are going back. We call as the swash and backwash processes, and through that process we get seaward inclined laminae, very gentle laminae. Definitely I am not going to the detail of each and every environments over here, because we don't have that much of scope of going into that detail. So definitely within the foreshore area, we get a lot of other processes associated with this, which I am not discussing over here. Just broadly, I am trying to give you a brief idea about what is the difference between individual areas in terms of the processes and in terms of the products. So in any shore environment, ideally, we can expect this kind of variations of facies types starting from offshore to onshore direction. So if I talk about the offshore followed by offshore transition, lower shore phase, upper shore phase, then foreshore, we commonly get a coarsening upward succession, where gradually the sand proportion is increasing, which indicates gradual increase in energy condition, and also that shows that the dominance of sand is more over mud in that overall succession. Similarly, we can take another example of a tidal flat. Again, a tidal flat is in the marginal marine environment, where from the shoreline we get a flat area separated by some barrier bars. So these barrier bars act as barrier to the open marine waves. So, waves get obstructed over here. So, we get a beach formed in front of these barrier bars, and this area is completely isolated from the open marine conditions. If that area is tidally affected, commonly we call it as macro tidal environment or maybe to some extent mesotidal environment, where every day we get a tidal fluctuation of 2 to 4 meter or even more than 4 meter, 6 meter, 8 meter fluctuation of tidal water level. So, in those areas during high tide condition, water enters through these gaps which act as channels, and we get several channels filling up this area. So, through these channels water comes in and covers up this entire area. We call it as a flood current, and then the water stays over there for some time during high tide, and then the low tide starts, and during that time water goes out and it uses these channels again. We call it as ebb current. So, every day during this tidal fluctuation in this kind of tidal flats, we get a bidirectional flow in terms of flood current and ebb current. So, during flood current water enters into this area and covers up this entire area, and then gradually it goes out during the low tide and the area gets exposed almost everywhere or maybe partially. So, depending on this fluctuation and this tidal range, how much it is covered up, how much it is filled up during high tide and low tide condition, we can divide it into subtidal, which is mostly this area where it is below the low tide level. We can get intertidal flat, which lies between high tide and low tide level. So, during high tide that area is entirely covered up by water, during low tide this area is exposed. The subtidal area can have water cover even during the low tide condition. And then we can get the supratidal, which is dominantly the landward side of the tidal flat, where we get very low energy condition. Commonly at very high tide condition, a very thin film of water can come up to this and remain over there for some time, or maybe these are sort of isolated areas, and there during high tides water can come in and get stuck over there, it cannot come out, and we get a swampy condition developed over there. So, in terms of the energy condition, we get maximum energy in the subtidal area, a moderate energy condition or fluctuating energy condition in the intertidal area, and a very low energy condition in the supratidal area. So, exactly the opposite type of energy distribution if we compare this with respect to the shore environment. In the shore environment, maximum energy is near to the shore, and as we move away from the shore, the energy condition gradually decreases. Whereas in this case, the energy condition is maximum away from the shores and its minimum near to the shores. So, in this case, what we can expect, the subtidal area, it is associated with high energy flow confined within the channels. Most of them are meandering channels. So, what we expect, the bars which are forming in these meandering channels, we can get multiple bars forming. So, these bars are getting affected twice. When we are getting water flow towards the land, we are getting deposition along this direction. When it is getting affected by ebb current during the low tide, deposition is going on in these directions. So, effectively what we expect here is this kind of bidirectional cross bedding, and sometimes it can be herringbone cross stratification. Many times we can get this kind of double mud drapes, large scale trough cross stratification, and also planar tabular cross stratification of different types, and each of them are covered with mud deposition. Each sand laminae is covered with a mud deposition. Commonly we call them as tidal bundles. So, frequent tidal bundles form within the cross beds, and those cross beds further accrete with each other through multiple reactivation surfaces. So, that is the characteristic of subtidal area, and very frequently we can expect this kind of bidirectionality in the cross beds, leading to formation of herringbone cross stratification in certain cases. If we compare with intertidal flat, it is a low energy zone with respect to subtidal flat. So, here also we are getting some channels, but these channels are low energy, smaller channels, depth of the channel is lower, and also the flow is getting weaker as the flow is moving upstream during high tide condition. So, what we expect, near to the subtidal intertidal interface mixing zone, there we can get some sand beds are deposited, and within those sand beds, particularly when they are deposited within the channels, we can get bidirectionality. Sometimes we can get some isolated sand beds leading to formation of flesser bedding, wavy bedding, lenticular bedding, and gradually as we move towards the upper part of the intertidal flat, there the mud proportion increases with respect to sand. So, the mud is to sand ratio that increases, and sand beds are commonly get isolated, ripple forms they get isolated. So, we get varied type of ripple forms within this kind of areas, and ripple forms formed in different orientations. So, organisms they prefer to stay in this kind of area because this is a very low energy zone where you have lot of nutrient supply, you have lot of light available, you have regular water supply available, as well as you have preferable substrate conditions. So, we get lot of burrow preserved over here, particularly within the mudstone dominated areas, as well as we get burrows within the sandstones. So, this part, the intertidal flat is completely different in terms of the facies types, facies associations, if I compare that with respect to subtidal flat. And then we come to the supratidal flat where the sand supply is almost absent, and then we get commonly mudstone which is getting deposited over there under a very low energy condition for long time. So, very often vegetation also develops over there, and thus the mudstone or this mud deposited, they are commonly associated with plant roots. They are extremely highly burrowed by different organisms, and sometimes if that is a swampy area, we can get coal. So, overall what we are getting in case of a tidal flat environment, it is an overall fining upward succession starting from subtidal to intertidal to supratidal. So, in terms of characteristic, a tidal flat, its characteristic features, its characteristic facies and facies associations are completely different from a shore environment. Again, if we compare the shore environment and the tidal flat environment with a fluvial system, say a meandering river system or a braided river system, again it is a completely different scenario. So, for each and every depositional environment, we have a separate depositional setting, separate depositional processes are going on, and following that process response model, we can have a different set of responses. So, a facies model is trying to represent those responses considering the processes as ideal processes which should go on in a particular depositional environment. So, definitely in all tidal flats we will not get similar kind of depositional pattern, it will vary because the dimension of the channels, the energy condition of the flood current and ebb current in those channels, the overall distribution pattern of the subtidal, intertidal flats, everything will vary. And depending on that variation, the distribution of these individual facies types and the facies associations characteristic of that particular depositional environment will definitely vary. But we can compare that case with this ideal model, and then we can get idea that what are actually varying, what are the processes varying in our case study, and we can understand or it will help us in our interpretation. Similar kind of scenario can be observed from deep marine environment where we can get a turbidite deposit. This is an ideal turbidite deposit. Turbidite deposit forms through turbidity currents, and this kind of successions are known as Balmer succession. So, this is a very famous one, and again we get different types of facies formed one after another, showing a gradual change in the energy condition within one turbidity current. So, ideally we expect this kind of distribution of facies types within one turbidity current. Now, in the deep marine part, we can get subsequent turbidity currents are coming in one after another, and they are depositing these materials. So, in each of them we expect this kind of distribution, and this distribution is in terms of the coarser beds, that is facies A over here, then facies B, then facies C, then facies D, and in that way it goes on. So, for each of them we will get this kind of lateral distribution of the facies types for each and every turbidity current. So, though this one is considered as the ideal one proposed by Balmer, actually from turbidity current what we get is bottom truncated or top truncated successions. So, top truncated commonly formed in the proximal part within the deep basinal area, proximal part with respect to the source area of the turbidity currents, and there we get mostly the dominance of lower units formed under high energy condition. Whereas, if we go to the further distal part, there we get dominance of these units which we call as bottom truncated units, that is the bottom portions are absent. So, ideally Balmer sequence is very rare, but we can get idea about the distribution of different facies types that can form from ideal turbidites in the deep basinal part. Similar kind of examples I can show you from the deltaic environment. This is an example of a deltaic environment where depending on the major dominance, we can get a fluvial dominated, wave dominated or tide dominated delta. So, as we know that a delta where a river is coming in near to the shoreline and it is debouching the sediments over here, and depending on that we can get different mouth bars forming over here. Also we get these channels distributed into several smaller channels, call them as distributary channels, and definitely if I make a section we get a delta plane initially, a delta plane where the river water is flowing, then it comes to the mouth bar area which is these mouth bars, and then it comes down to the delta front area. So, this delta front area further goes to the deeper part which we call as the pro delta area. So, delta plane, delta front and pro delta, these are the three different units or three different sub environments that we commonly get in case of a delta. So, definitely the conditions are different, and already we have discussed about this delta as an example in our previous class on the facies association. So, I am not going to the detailed discussion again over here, but this will be the different types of facies model for a delta. These are some examples, and you can see over here based on which one is dominant, whether it is a tide dominated or wave dominated or fluvial dominated, the nature of distribution of facies is changing within the delta systems. So, again these examples are not exactly ideal for a delta system, but we can consider them as the facies model for tide dominated, wave dominated or fluvial dominated delta system, and we can compare this with any other case across any other part of the world. So, through facies models what we can get is a normative and idealized model which represents the idealized conditions or processes going on in a particular sedimentary environment, and that helps us to compare, that helps us to interpret or understand. So, how can we make a facies model? What are the rules to make a facies model? The first step is we have to go through all the beds, we have to assign a facies to all such beds which are available, and then we have to club them into facies associations based on their genetic relationship. So, for that purpose we have to look at the pattern of distribution of the facies types vertically and laterally, temporally, spatially, and then based on that we try to correlate them across the basin in terms of facies associations, which actually give us idea that the processes together are occurring or several conditions or a set of conditions occurring in that particular depositional environment, both laterally as well as vertically, and based on that we try to interpret the depositional environment. In that facies analysis flow chart in our previous class, I have already told you that what are the steps that we follow. One component was there, the comparison with the facies model. So, in this particular class I have tried to give you a brief idea about this facies model concept and what we actually try to understand or interpret from facies models. So, these are some of the references or some of the books that you can further follow for detailed study. So, thank you everyone.